Welcome to Lecture 5 of Week 6 of Math 320. In the last lecture, we gave some theorems concerning subsequences in general. Today, our focus will be on a collection of theorems concerning subsequences of bounded sequences. The first theorem says that if x sub n is a bounded sequence, then the limsup and liminf are both subsequential limits. Notice that, as we discussed before in week 5, for any bounded sequence, there exists a limsup and a liminf, thanks to the order completeness of the real numbers. So the key part of this theorem is that the values limsup and liminf can be achieved as subsequential limits. For the convenience of exposition, in the next slide, we will use z sub u to denote the value of limsup. Here's the proof for the case of the limsup. I'll leave the case of liminf as an exercise. Remember, to show that a value is a subsequential limit, it is enough to show that for every epsilon there are infinitely many terms of the sequence within epsilon of the value. So, we start by letting epsilon be positive. Necessarily, z sub u plus epsilon is an eventual upper bound, since z sub u, or the limsup, is the infimum of all eventual upper bounds. This means that there is a capital N such that x sub n is less than z sub u plus epsilon for all n greater than capital N. Similarly, z sub u minus epsilon is not an eventual upper bound. This means that for every capital M, there is a subsequent term that is more than z sub u minus epsilon. Combining steps 2 and 3, we see that there are infinitely many terms of the sequence with index bigger than capital N, such that the term is both less than zu minus epsilon and greater than zu minus epsilon. This means that there must be infinitely many terms of the sequence that are within epsilon distance of zu, showing that it must be a subsequential limit. The key to this proof is in step 4, where we combine steps 2 to 3. You may wish to pause the video for a moment to think through how it works. A consequence of this theorem is the Bolzano-Weierstrass theorem, which asserts that bounded sequences have convergent subsequences. This follows because every bounded sequence has a limsup, and we just proved that a limsup has to be a subsequential limit, which by definition means that there is a subsequence that converges to limsup. Interestingly, an alternative proof of the Bolzano-Weierstrass theorem can be given using what we learned from the last lecture. If you first apply the theorem on the existence of monotone subsequences, and then the monotone convergence theorem, you will also locate a convergent subsequence. The difference is that in this alternative proof, the subsequence is guaranteed to be monotone, but we have no control on what its limit is. In the proof using the first theorem we just discussed now, we know precisely what the limit is of this subsequence, since we can set it to equal to either the limsup or the liminf. The second theorem of today extends on what we previously discussed last week concerning limsup and liminf. Then, we prove that for a bounded sequence, its limsup is below that of its liminf is below that of its limsup. Thinking in terms of their definitions as the bottom of eventual upper bounds and the top of eventual lower bounds, we may find the following theorem rather intuitive. It says that for any bounded sequence, any subsequential limit has to be between the limsup and the liminf. I will just give the proof here showing that the subsequential limit cannot be less than liminf. You should try to write out the proof for z not being greater than limsup. What we will prove is that any z that is less than liminf cannot, in fact, be a subsequential limit. So, start with taking an arbitrary z less than liminf. Let epsilon be 1/2 the distance from z to the liminf. And so we know that z plus epsilon is between z and liminf. Since z plus epsilon is less than liminf, we know that it must be an eventual lower bound. Therefore, there exists some capital N such that for every subsequent index, x sub n is above z plus epsilon. Because of this, there cannot be more than n elements of the sequence that is within an epsilon distance of z. Since this set is finite, by theorem 52 again, we see that z is not a subsequential limit. Thanks to theorem 52 describing subsequential limits, this proof is extremely streamlined and sleek. Do make sure you are following the logic. And finally, the third theorem of today and the last theorem of this week. This one says that for a bounded sequence, if its set of all subsequential limits contains only one point, then it converges. First, note that boundedness is crucial here. Consider the sequence that goes 0, 1, 0, 2, 0, 3, 0, 4, 0, 5, and so on. This sequence is unbounded and hence divergent, but the only subsequential limit it has is the point 0. This theorem should also be compared to the first theorem we proved in lecture 4. There, we showed that if a sequence converges to a number z, then all of its subsequences also converge to z. Recalling that we have also proven previously that all convergent sequences are bounded, and we see that these three theorems can be combined into an if and only if statement. A sequence converges to z if and only if it is bounded and all of its subsequential limits equals z. Okay, let's finish up and give the proof. Using the first result of today, we notice that both limsup and liminf have to be subsequential limits. By the hypothesis of this theorem, there is only one possible value for the subsequential limit. So we are forced to conclude that limsup is equal to liminf. Returning to theorem 45 that we proved last week, this means that the sequence must converge, with the limit equaling the common value shared by limsup and liminf. Okay, that's it for this week. Next week, we will finish up our discussion of sequences by returning to a few more features about the limsup and liminf. A lot of what we will discuss already appeared in one way or another in the lectures from this week and last. What we will do next week is to summarize and collect some of these properties. See ya!